Okay, there's the circuit that we're going to be testing. This is the Ainslie, I don't know, whatever you want to call it, crossover thing, exactly as she's drawn it. I've inserted a couple of LEDs. Well, I've tried this arrangement of LEDs. Right now I've only got one there, and I've got another one just completely across the load. And I'm going to be interrupting the supply to the battery right there as part of the demonstration. And I'll be using two N7000 MOSFETs instead of the more expensive IRF PG50s. And I'll be using a 3-volt battery supply made out of those guys there. And there is the actual instantiation of the circuit. Now, I've found some interesting things about this circuit. One is that it's very insensitive to the value of the inductance and the load, and it's very insensitive to the frequency that's being supplied by the function generator. And there's some other interesting things going on that we'll see pretty soon. Now, at my location here, I don't have access to a fancy digital oscilloscope, so I'm relying on my trusty rusty old HP 180 right there, and for the signal generator I'm using my Interstate F34 F43 high voltage function generator right there. Okay. And by high voltage it just means that under optimal conditions it can generate a relatively high peak-to-peak voltage, 20 or sometimes even 40 peak-to-peak. But it's as you'll see, it can't sustain that voltage into this circuit. All right. So right now I've got the function generator not hooked up. I'm preparing to hook it up, and I'm monitoring the battery voltage actually. So what's shown on here is channel 2. This is what we're looking at with the oscilloscope right now, looking right across the battery. And that's going to be displayed up here on channel A of the scope, and I've marked the 0 line there for you. Channel B will be monitoring the output of the function generator. So I've marked the 0 line there on channel B, and let's see, let's go ahead and switch that channel on, and there you see the square wave that the function generator is putting out, and you can see right now that it's swinging plus and minus 10 volts. I'm sorry about the light. But anyway, that's on the 10 volt per division scale, and we have no attenuation. So right now it's swinging plus or minus 10 volts around that 0. And I have a DC offset knob right here, and so if I pull that knob and crank it, I can move the signal to all negative, that's 0 to minus 20 volts, or all positives, except I lose the scope trigger there, but say 0 to plus 20 volts. But we'll keep it plus or minus 10 right now. Okay. And that's just by moving the offset knob here. We're operating the function generator right now at a frequency of 1 kilohertz, 1K times the setting of the function generator, and we're of course doing a square wave, 50% duty cycle square wave. Alright, now what I'm going to do is just hook the function generator in to the circuit. I'm just going to just go ahead and hook it in. The batteries, as you can see, are still not connected. The battery's out, so it's series through here, so if I separate one battery, then the batteries are effectively out of the circuit. Alright, so I'm going to hook up the function generator like that, and it's wired in just exactly as it is here. Okay, so here's the trace, so boom. You can see how the voltage on the scope screen drops radically. What that means is that the circuit is actually loading the function generator. The power from the function generator is doing a lot more than just switching these very high impedance gates. It's going in there somewhere and heating up the MOSFETs. So as you can see, we've dropped down to about 5 volts peak to peak. So what I'm going to do is turn up the output of the function generator so we have a decent, actually that's the maximum output of this function generator right now, there. And we're getting such a voltage drop because the circuit is using power, it's using power that the function generator is putting out. Alright, so now let's go ahead and, still without the battery connected, let's take a look at what the battery voltage that is here with the battery disconnected. So I'm going to be monitoring here, but I've broken the battery contact there. Alright, so let's turn that on. Boom. Now you can see, well, even before I turn it on, you can see that there's a little bit of a parasitic oscillation in there. Alright, and that's just crosstalk between the oscilloscope channels. If I turn it on, you can see, lo and behold, the output voltage follows the stimulus of the oscilloscope. And if I move the offset of the oscilloscope, you can see that the voltage that would be fed to the battery is also changing. Alright, now that one is on 0.5 and it's a 10x attenuating probe. So what we actually have there is 5 volts per division. We're getting the same input on the output that the function generator is putting in. So that's where all that power is going. It's going through the load and bouncing around in there. And even though the battery is disconnected, there's no closed circuit through there. That's still what's going on. Okay, now what I'm going to do now is just put the battery in like this. Alright. Zap. Okay, so now what do we see? We see that the voltage has gone up from 0 to 3 volts all the way across the top, because that's the battery voltage. But what about the oscillations? There's a little bit of a thickness of the line right in there, and if I vary the function generator offset, I don't know if that's showing up very well, you can see that the thickness of the line is here when the offset is down low, but when I move the offset up, that line thickness moves to the other phase up there. Alright. So that oscillation is actually coming from the function generator. Alright, if I remove the battery again, alright, like that, you can see how those lines get thicker as I change the offset. And if I reduce the power of the function generator, all of that oscillation goes away, even with the battery disconnected. Isn't that interesting? Now with the battery disconnected, the MOSFETs, both of them actually, also get hot. Earlier I said that only one of them was getting hot. I was measuring it with my little IR non-contact thermometer here, and it turns out that the laser spot is actually off a little bit. So when I hit that MOSFET with the laser spot there, I'm actually reading this MOSFET. And so to read that MOSFET, I got to move over to the left a little bit, and there, right around there, you can see that it's warming up there too. So I got both MOSFETs here are getting kind of hot, and that is without the battery in there. Okay, so this circuit is running mostly on the function generator. Now here's an interesting thing. You can see the LEDs, right? Let me turn off the, whoops, that doesn't work. Let me leave the light on. Okay, you see those LEDs without the battery in there, and I go to vary the offset, up and down, up and down, like that. Nothing happens to those LEDs. But then when I put the battery in there, like that, and now I vary the offset, I guess you can see, varying the offset, one, both. That one there is on the secondary of the inductor, so it's actually responding to an AC current. The one on the top is across the primary of the inductor. And what I'm doing is, of course, just varying the offset, the DC offset a little bit. And okay, so that LED lighting doesn't occur when the battery is out of the circuit. All right, here we go again. Battery out of the circuit, and turn off the lights and vary the offset. You see there's no LED lighting at all there. So the presence of the battery in the circuit does allow completion of the circuit flow enough to cause those LEDs to light up as I vary the offset. Okay, so the bottom line to take home from this is that the circuit is oscillating because it's hooked up to a function generator, and the function generator is actually powering sufficient power to make the MOSFETs oscillate. Thanks for watching.